Hello everyone and welcome to our today's webinar and our seminar about optical measurement systems in combination with shaker testing. Very warm welcome, and warm especially because in some regions of Europe it is very cold these days. My name is Martin Engelke from IMV, and I'm very pleased to introduce my guest today, Mr. Ralf Lichtenberger from Limes.
Yeah, good morning, everybody, also from my side. I welcome you to our webinar. Thank you at this point for the organization to Martin. Thanks.
Ralf, you studied physics at the University of Karlsruhe at the KIT, and you've been a researcher for 5 years at the KIT in the field of optical measurement technologies and deformation measurement. And then you've established long ago already, in the last century, Limes GmbH in 1998, with a focus on development and sales of camera-based measuring systems. And so you've become an expert in the field of digital image correlation for material and component testing. And as you're an expert, and I'm not, I'm very pleased to have you here today to explain a little bit about the benefits, solutions that optical measurement systems do offer nowadays. I remember when I started in a vibration laboratory around 2000, the year 2000, we were also always looking for application of camera-based systems for our shakers, and we are in regular contact. And now what I've learned, what has been evolved or has evolved in the last couple of years is just amazing. So I'm really looking forward to your presentation and explanation about optical measurement systems.
Yes,
over to you.
Thank you for the invitation. So, the title of the presentation or the webinar is Using Optical Measurement Systems for Shaker Applications. And indeed, I have spent probably close half of my life with camera measurement systems, more cameras than optical measurement systems. So I don't want to say that I'm an expert, but I have a little bit experience in this field. And this course set actually as a spin-off from university, we have started to found a company called Limes. And we have spent all the time in the last years to develop camera-based measurement systems. Actually, our company is split up in two parts. One part is developing, selling, manufacturing camera measurement systems. It's partly DIC systems for deformation measurements, video sensorimeters for material testing, and also a Strobe Cam system for vibration analysis. And the other part of our company, it's selling and doing service measurements with 3D laser scanners. So I'm responsible here for the left part, for the camera-based system part, and this is about what I want to talk about today.
Very good. We can see a lot of systems, and I know from experience and from knowing you that there are a lot of different technologies. Just a note, because we are showing a presentation here at the end of this interview, we are going to share this with the attendees, aren't we? So,
yeah.
So what are the different technologies that could be used, especially for environmental testing, in your experience?
Okay, besides the systems that we are using for vibration testing, I have done a little bit research, and I have come over a few more systems that are on the market. And let's have a brief overview about those technologies. So I call it optical technologies because it's partly camera-based, partly with a human eye, partly with lasers. So just an overview, and we can quickly go over those systems. So the most simple systems that you probably all know is a strobe light. Strobe lights are manufactured by many companies in Germany and everywhere. So it's in principle, I will explain a little bit later, probably this is just for the overview. I have also added Strobe Cam, which is a camera-based system for visualization of vibrations to our overview. I have added high-speed camera. We know that some customers are using high-speed cameras for vibration measurement. And I have added 3D DIC, which is a very powerful and very accurate technology to measure deformations, displacements in 3D and also mode shapes. You'll learn about that later in detail. And I have added laser vibrometers. It's also an optical technology. It's a laser interferometric technology, so it's very accurate and so on. This is an overview that I have summarized for this presentation, and I hope that I cover almost all that is on the market available.
So that's not only your products, but really we wanted to discuss about technologies for shaker applications. So we are covering a wide range today, and we have a big audience today. So I will be interested. Do you have already experience with the equipment we are discussing today? So feel free to have a look at our poll. I've just started. So interested to see what's going on. Yeah, should we start with explaining the technologies in a little bit more detail?
Yes. For those who have no experience with techniques, I have added a few slides to conclude how they work and to explain how they work. So first of all, let's start with a strobe light. A strobe light is more or less a very powerful pulsed light, and the light duration is very short. The frequency can be very high nowadays, a few kilohertz. And the idea is to illuminate the object more or less with the same frequencies and the object is moving. And this is causing such called stroboscopic effect. So we can then see a motion of an object in slow motion. Typically, it's used just for a bare visualization with the eye, but you could use your mobile cam or a smartphone cam to record what you are seeing.
Would that work when you use your mobile phone? Because the recording frame rate might just be different.
Probably it doesn't work every time. I have seen videos where it works with mobile phones. It probably depends also on the frame rate of the mobile phone. It depends on also on the shutter time, on the exposure time of the camera. So it's quite complex. It's an optional possibility to add a camera. It could be also in an industrial camera or a high quality camera, video camera. But on those cameras, of course, you have not the possibility to adjust parameters like exposure time, brightness, and so on. So it's an automatic process, and it may fail. So strobe light is made for visualization with your eyes, and a camera might work. And I have seen working videos. So actually, I have found a video on YouTube that we are now presenting, and it's showing a beam on a shaker that is running with this eigenfrequency. And of course, the recording is done with a camera, with a video camera. And what you can see is that the light flashes are now in the frequency very close, not exactly identical, but very close to the frequency of the movement. And this allows us to see the eigenfrequency motion in slow motion. Yeah?
Does it need to be dark in the laboratory?
Yes, you need. Nowadays, of course, those strobe lights are very powerful, and you can spend a couple of €1,000 for getting a lot of light. But it is necessary that your environment is dark to see the movement in good quality. And of course, you have seen on the YouTube video, which is about 8 or 9 years old, I have seen, that the quality is not very high. So the camera resolution is probably 300 by 300. Nowadays, we can use for those applications much higher resolution cameras. So we get more details to see.
Great.
Yeah.
Just back to the poll, we can see that we have a lot of, so everybody is here. So we have experienced users, we have users who are new to this topic. So it's great that we are covering such a great range here in our interview today. So I hope that for everyone attending is something as a takeaway.
Yes, I'm especially keen on the last answer. No, not yet.
Okay. One question is, yes, I'm using a shaker system. I am since a long time, and it's always, I think for me, it has been very interesting to see, as I said in the beginning, in the introduction, that things are changing. The technology has developed so fast, camera-based system. I think we'll see some examples later, which really were awesome. So, okay.
Okay. So there is not much more to talk about a strobe light. It's a light and it's flashing very short with a specific frequency. That is the secret of strobe lights.
Yeah. I think with optical systems, if you want to visualize the movement of your specimen, it does have to do a specific movement so that you can really spot that with your eyes.
Yes, exactly. So you can only see a movement if it's large enough to be visible. You cannot see a micrometer movement with your bare eye. Even with a camera, it's difficult to see that. But using the word camera, this brings us to the next technology we have found. We call our system Strobe Cam or Strobe camera. You will find other systems in the market. They are called sometimes video stroboscope. And in principle, it's a technology where we are using a constant light, which is more comfortable for the human user if the light is constant. And we are using a very short exposure time of the camera to freeze the motion. This allows us to have a real-time visualization on a monitor. And it's also possible to record those images or videos. So you can really do a logging of your testing with this kind of technology. And as you have images or videos, you can analyze those optionally with 2D motion analysis. And from that, you probably can get also more information than just by looking on a video, on an image. I think I have also added an example for that.
That one?
Yes, exactly. So that's what you have probably seen on LinkedIn as an invitation. So it's a metal blade that is shaking with different icon frequencies. You can see the frequency displayed in the top. And this is now what you see is just different icon frequencies and what such a camera visualization has recorded and written as an AVI file. So you see at different icon frequencies, the movement of the object is different at higher frequencies. The tiny parts are moving at smaller frequencies. There is a global movement of the object. That is what you should realize. And a camera system, a video stroboscope or a strobe cam system is used for visualization. So it's very beautiful. It has a high quality and you can directly see what parts on your object is moving. Mm-hmm. Of course, this is a very simple example. It's just a metal blade with different holes, but it has different icon frequencies. So it's a complex object in terms of shaker measurement.
Sure.
So I think this is understood. We can visualize movements with different frequencies. And you have probably realized that independently on the eigenfrequency, the movement speed, the slow motion visualization is constant. This is what we can set up in such a system. And independent if an object moves with 1 kilohertz or with 100 hertz or with 10 hertz, the visualization has the same frequency, which makes it more clear for the human eye.
Okay.
I think there is also a second video that I have added, because a nice thing here is that you can use this technology also for frequency sweeps. As a previous example, you have seen fixed frequencies, eigenfrequencies, and now you see a video that is recorded during a frequency sweep. The frequency started at about 20 hertz, and I can't remember at up to what frequency it goes, but you see the frequency displayed in the video on the top left corner. So, and you see, depending on the frequency, this spring is moving in different directions and different eigen modes are accelerated. So here, for example, there is an eigenfrequency at about 130 hertz. Now we have a lateral movement, a little bit higher frequency. And you see also some stickers, 1, 2, 3, on the video, and we have applied those stickers, which are very lightweight, so they don't influence the vibration of the object in this case. But we have applied those stickers to do some post-processing. We can do very accurate displacement measurements from those videos. And when this video is finished, we can show something like a resonance curve that shows the horizontal and the vertical displacement of the 3 dots. Mm-hmm. I think I just need to go to the next slide. Oh no, actually, I'm wrong in my counting. I explain how it works at a later stage. So this is a result of what we should see. And I will explain in detail how this technology works. So now you get the visualization before the technology. And that's what the displacement measurement gave us. So we have some horizontal movement, we have some vertical movement of the spring, we have the 3 dots tracks, and here you can see the different eigen frequencies of the different directions. I'm sorry for this jumping. So let's go back.
Keeping us awake. Yes,
let's go back to this slide. And how does this work? It works by a very precise synchronization of the camera to the shaker signal, to the frequency controller or frequency generator output. So every frequency generator has a cola signal output, which is proportional to the acceleration of the shaker. And we have developed an electronics. It's a microcontroller unit that is receiving this cola signal as an input signal, analog input signal, and is generating very accurately, phase related to this input signal, a trigger signal for the camera. And the camera records an image always when it receives a trigger signal. How does this work in practice? So for example, we have a sinusoidal cola signal, and we want to record images at a specific fixed phase. So this technology allows us to set up a specific phase difference between the cola signal and the camera. So which means...
Where do I set up this phase difference? Because a vibration controller is putting out the constant sine wave with a constant amplitude with the same frequency the shaker is driven.
Yeah, so
that's a phase.
The cola signal is analyzed with this microcontroller, and this microcontroller permanently measures the amplitude of the color signal, and it measures also the frequency of the color signal. So it knows exactly when is phase 0. Okay. And related to this phase 0, which is phase 0 on a sinus signal, which is here the 0 value, related to this 0 value, we define phase 0, and the trigger unit is defining a trigger phase related to the 0 signal, which means this trigger unit is doing everything automatically. It can be programmed by the user interface of the Strobe Cam software, or set up by the user interface of the Strobe Cam setup software, and you can define with which frequency the camera is running. You can define the slow motion frequency, but the secret here is really that it is very accurately phase-related triggering the camera to the periodic signal of the frequency generator. Mm-hmm. And you can imagine, as we have such a precise synchronization, when the phase triggers always at the same phase value, we don't see any movement of the object, because the object is always in the same location. But when we change the phases, and this trigger unit can do this automatically, when we change the phases, we see, so in the top, oh, it doesn't show a video. Okay. The top image should show a constant image without any movement. And this is because in the top setup, the camera is triggered always exactly at the green line at a constant phase. In the bottom setup, the trigger of the camera is always received at a slightly incremented phase. Mm-hmm. And if we change the phase a little bit, we can see a visualization. And actually, you have seen this in the previous videos. So the presentation here, the video on the bottom is not moving, but it should move. It should show a moving PCB board with visualized with a slow velocity. Yeah. I hope that this is understood. So the secret here in this Strobe Cam is a very accurate phase synchronization, phase triggering to the related generator output signal. And with this, you have seen already the videos. It's possible to visualize movements on eigenfrequencies or even on a frequency sweep. And the system is optimized to produce small videos, which means if you have a frequency sweep of, let's say, 5 minutes, mm-hmm. The system will record about 5 megabyte image data, even with a HD camera with a 2 megapixel resolution, which is a very high resolution for this application and can give us a lot of interesting visualizations.
So did you say that the whole 5 minute sweep just produces 5 megabyte picture data? That does not sound much.
Yeah, it's a compressed video. Okay. And we are using a high quality codec to compress the video. And in those modern codecs, the videos always record differences. Mm-hmm. And if you have no difference, 1000 images needs the same amount of memory as one image. And those modern AVI codecs, we typically record the images as AVI files. They produce very small video sizes with very high quality, actually.
So I remember that when you want to do high frequency stroboscope camera recordings for your video, in the past you needed very bright lights. So how is it today? What is the maximum frequency of this strobe camera, and what about providing the correct and good light?
So the experience is that with our standard lights that we equip with our strobe cam, we typically can go up to 2 kilohertz or 3 kilohertz. If the frequencies that we need to visualize are much, much higher, we need to add a second light or to use even a little bit more bright special lights dedicated for high-speed camera recording, for example. But of course, it's a camera technique. So, and we are using very short exposure times to freeze the movement. And you have seen on one of the videos that the small parts of this metal plate has moved with 1900 hertz. And to freeze the movement, we need to use a very short exposure time. Otherwise, you would see a motion blurred object. So typically, the strobe camera is equipped with good light, but also due to the fact that modern cameras are very light sensitive and can support binning modes and more sophisticated ways to increase the sensitivity electronically. It is possible to go up to a couple of kilohertz with a standard light.
Nice.
And that is typically sufficient. The automotive industry is typically testing up to 2 kilohertz.
Yeah, I think so.
That is no problem.
Huh. Sounds good. No problem is always a good statement.
Yeah, so as you have already seen the videos that produce a strobe cam, we can continue with the next technologies that I have added in our overview. And this is a high-speed camera. A high-speed camera has in principle the advantage that it can record very fast images and image sequences. So it is also used like a strobe cam for recording and for visualization. And as with the strobe cam system, we can additionally add 2D or 3D motion analysis to get frequency diagrams. The big difference to the strobe cam is that those cameras can be used also for non-periodic events. And typically high-speed cameras are used for crash tests, for drop tests, for impact testing, or for shock tests. And only with a high-speed camera, you can visualize a shock test on a shaker.
As if I knew that you were going to say that. We have prepared a video.
Yes, and this video I also wanted to show after the technical explanation, but
I'm sorry.
It's fine to see it here as well. So this is a kind of shock test or a dop test. So it's a PCB board that impacts, and you see that the capacities on the PCB board, they are beginning to shake. And of course, this is now a visual representation of what the high-speed camera has recorded. And if we go back to the presentation, you can, thanks. If we go back to the presentation, if we jump over this slide, we will see here the result of the motion analysis. And what you see here, we get the displacement velocities and the accelerations of the PCB board and of the single capacities also on different directions. So it provides quantitative measurements on something like a shock test. But how is this technically possible? So jumping back, a high-speed camera, the secret of a high-speed camera is that it is using a very optimized CMOS sensor. It has an integrated computer, CPU, something like that, and an integrated memory. So the transfer from the camera sensor to the memory is very short. So it's a very dedicated interface where the sensor is read out in parallel. So it is possible to achieve very high data bandwidths from the sensor to the memory. And after the test is done, after the memory is written with images, you will need to read out these images from the high-speed camera over a dedicated interface like gigabit Ethernet or 10 gig E or other interfaces. But the initial storage is happening in the memory of the high-speed camera. And nowadays, those cameras, they can record up to 20 kilohertz at 1 megapixel resolution. Oh. They are very special cameras for even higher recording rates, but they are too expensive for strobe, for vibration measurements on shakers. So an advantage of those cameras is also that the pixels are very large. So they are very light sensitive, and you could use such a camera at 1 kilohertz recording rate without additional light, just by using the lab floor light.
Okay. I would have been thinking that a large pixel is a disadvantage.
It has also disadvantages, but in terms of light sensitivity, it's a big advantage. Okay. So I know those cameras, they have a pixel size of 20 micrometer, which is huge. And industrial camera has a pixel size of, let's say, 3 to 5 micrometer. And so as a pixel size goes in quadratic in the light sensitivity, such a camera is very nice in terms of light sensitivity.
Okay.
But it has also disadvantages if you think about optical aspects, depth of field, and so on. And the major disadvantage of this camera, of high-speed cameras, is that you have only a specific amount of memory. And this memory is maybe 16, 20, 32 or 64 or even more gigabyte of data, but this limits the high-speed camera to a recording time of a few seconds. So it's only dedicated for crash test. You can not do a frequency sweep test with this technology.
Nice.
Okay, and in our list we had also the DIC technology.
Yeah, that was quick because we've been showing the video. If we go one slide back, because that is something that I find amazing, because when we do a vibration test on a shaker, of course it's nice to have a video, but the question always is, I've seen a movement, how has the displacement been in reality? And also what we have seen with the stroboscope camera, that you can see at which frequency which displacement happened. So and this is again something you could provide nowadays.
Yes, whenever you use a camera for vibration testing, you have the option to add some post-processing. So you can do motion tracking, or you can use DIC for full field displacement measurement. And this always gives you quantitative data. And it is also using sophisticated algorithms, which means the sensitivity to resolve displacements is based on image analysis much higher than with your human eye.
Yes.
So if you use only a camera, you can visualize a movement, let's say, of the order of magnitude of 1 pixel. Using post-processing DIC, motion tracking, you can resolve typically a 50th or 100th pixel. So it makes the sensitivity much, much higher. And you can see maybe a small eigenfrequency with some micrometer amplitude. You can measure it, but you cannot see it.
Okay, nice. Yeah, that's amazing.
But whenever you use one camera, you are always limited to a measurement in the plane. So you cannot measure out of plane. It's not a 3D measurement. And this is where the 3D stereo camera systems are improving much more the informations, because we are using here 2 cameras, and this is a triangulation principle between the 2 camera views, based on DIC or based on photogrammetry. And these measurement systems, they provide a spatial resolved 3D displacement and deformation measurement. So it's providing 3D coordinate informations, 3D displacement information, and also strain. And it's a very nice technique, for example, to measure mode shapes on objects. And I have one slide to show in very briefly how this technology works. So it's based on, let's say, pattern tracking technology. So we need to have a random pattern on the object surface. And if we don't have a natural pattern on the surface, we could use a sticker or we could use a spray paint to produce a certain pattern on the object. And this pattern tracking technology or digital image correlation technology, it is capable to measure the motion and the deformation of the pattern inside a small, let's say, correlation window or subset. So the images is divided by the DIC software in small subsets, and the pattern inside every subset is giving, in this case, a 2D displacement and deformation value. And this technology nowadays is done typically with 2 cameras. And if we are using 2 cameras, we talk about stereo correlation. So which means the left camera records the object from a slightly different viewpoint than the right camera. And every surface point or its small surrounding is stereo correlated between the 2 cameras, between the left and the right camera. And this technique allows to get at as first state the shape, the 3D coordinates of every surface point of the object. And this stereo correlation is done for all images in our image sequence. So, which means for every image state, we get a 3D coordinate and relating the reference coordinates of the surfaces to the deformed or moved coordinates of the surface, we get the 3D displacement, the 3D deformation, and the surface strain. And the major advantage here is that it is very accurate. So we get micrometer resolution. Typically, we say, as a rule of thumb, such a technology can resolve 100,000 of the field of view width, which means if we have 100 millimeter field of view, 100,000 of 100 millimeter is 1 micrometer. So it's a very sensitive technique.
Yeah, I can see the 2 cameras in the upper right corner of this slide. Is it difficult to do the setup? So do you have the cameras at a specific distance with a specific angle towards the object?
No, it is very flexible to set up, and the cameras are typically set up to see the interesting surface points in both cameras. Mm-hmm. And of course, we need to focus the camera, we need to adjust the aperture. And after this is done, such a 3D system is calibrated with a checkerboard calibration plate. Okay. But that's an automatic process. And only when you change the optical setup of your stereo system, you need to do a calibration. This calibration process takes maybe 10 or 20 seconds. So it's very quick. And it's an automatic process. But this allows us to receive quantitative 3D measures. Without calibration, it's not possible to get 3D measures in millimeters.
Okay. We do have a video assigned to slide 19. Shall I
yes,
play that?
Yeah, please. So that video shows an aircraft model which is mounted on a very tiny shaker. So I think it's a 10 Newton shaker. And the videos that you see, it is a live video of the wing. And as an overlay on this live videos, you see the red grid displays the 3D displacement of the wing. And the amplitude is so tiny that we cannot see any movement in the camera. Mm-hmm. And the grid, it is accelerated by a factor of 50 to see the movement. And at the edge, at the corner of the wing, you see a point, And in the bottom diagram, you see the set displacement of this point quantitatively measured. And this is a measurement with a static high resolution 2 megapixel camera at an icon frequency of, I think it was 33 Hertz. So this wing has its first icon frequency at 33 Hertz, and our 10 Newton shaker can get out movement amplitude of 0.3 millimeters. So
yeah, I think that is an interesting thing, because when you say that you are usually testing aircrafts, you can imagine that the wing of the aircraft really is moving. But as you just said, there is with the eyes, there's no movement to be detected, but only in the post-processing you can find those modes. Is that correct?
Yeah, exactly. So the post-processing increases sensitivity roughly by a factor of 100. And the visual movement is below 1 pixel, so you cannot see it, but you can measure it.
Yeah, nice. Back to the presentation.
Yeah, back to the presentation. What else do we have here? So a second example, and this is an PCB board. You see the speckle pattern. We call the random pattern on the surface speckle pattern, which is sprayed on the PCB board with some electronic components, with a connector, with some integrated circuits. And if you imagine that you want to accelerate this PCB board with a pink noise, it is not possible to use a strobe light. It is not possible to use a strobe cam, because both of them needs a single frequency. And it's also not possible to use DIC with a phase trigger unit, because this is also limited to a eigenfrequency data. But if you use two high-speed cameras, as you see it on the stereo bar in the top right corner of the slide, it is possible to use DIC technology on pink noise stimulation on any specimen. And here is an example where we have applied a pink noise on this electronic board. The measurement rate of the camera was 2 kilohertz. And for this, we have also a video that you please show, Martin. So it's mode shape analysis. Q400 is our product name, 3D DIC. And when the video is running, you see our PCB board, all the grid points that are measured. We need to select a couple of points where we expect some movement. In this case, we have selected 4 points. So what you see, this is the displacement, the set displacement of the 4 points in time domain. And if we do a Fourier transformation, we get the frequency responses. And here we can select some eigenfrequencies that are interesting for us. So the red point has some eigenfrequencies at different frequencies. And if we do some mode shape analysis here, we see the movement of different eigen modes of this PCB board. So you see at the top of the slides, the frequencies are changing, and I have just added the analysis of all different eigenfrequencies to this video. Maybe you want to run it again because it's so beautiful. I think it's beautiful. I hope you like it as well.
Let me restart it.
So I have just added some results to one video, which is more efficient than starting 5 videos. So this is the time response, the frequency response. So different points has different eigenfrequencies. And if we then do at those 4 different, we have selected 4 different frequencies. If we then do a mode shape analysis, we get these different eigenmodes.
Okay.
And mode shapes.
Yeah, maybe I've started a poll some time ago asking our audience, do you know the Nyquist frequency? And you said, you have been using a random test up to 2 kilohertz. So what does that have to do with the Nyquist frequency and the results we are seeing here?
Yes.
if there is a relation.
And I'm happy that we have 37% not knowing what is Nyquist frequency. So there is a Nyquist theorem, and it says that you need to measure with a 2.5 higher frequency that you want to resolve as a vibration. Example, if you want to measure up to 1 kilohertz movement, you need to record with a high-speed camera faster than 2.5 kilohertz. So factor 2.5, which means the Nyquist frequency, I think the Nyquist frequency is a frequency that you can maximum detect using a specific recording rate of the camera. This means, in my last sentences, if you are using 2 kilohertz measurement rate, you are getting close to 2 kilohertz vibration sensitivity, maybe 1.8. I cannot calculate 2 divided by 2.5 with my brain. I would need to use a calculator for that. But thanks for the responses. I hope that this is now more clear. So we need always to be more fast with the cameras than the maximum frequency we want to resolve with our measurement.
Okay.
So, and yes, the last technology I'm stumbled over is laser vibrometer. This is more or less a displacement sensor. It is not directly able to measure strain, but it can measure at a single point or at multiple points out of plane displacement, or if you combine multiple laser vibrometer, you can also measure 3D displacement. So a scanning laser vibrometer scans the surface, and then you get also a full field displacement information. And it's typically used for mode shape analysis as well. How does this work? I don't want to answer this in detail. So it's a laser vibrometer is based on a laser Doppler vibrometry. So we are this technology uses a laser, a Bruxelles, and so on. And laser Doppler vibrometry means that when the object moves in direction of the laser vibrometer, the frequency of the laser changes. It gets larger or smaller, I don't know. But it changes in the other direction than if the object would move away. So the movement speed is related to the frequencies that the detector in the laser vibrometer is detecting. And from that, it's possible to measure displacements, displacement speeds, and also amplitudes, of course, by integrating this. And by using multiple laser vibrometers, you get also 3D information from that. The great thing in laser vibrometer is that those systems are very accurate and can go up to very high frequencies. And maybe it's a little bit an overshoot on testing on electrodynamic shakers, where we are talking about a few kilohertz. This technique can go up to gigahertz, which is 1,000 times faster than required on electrodynamic shakers. But I wanted to show it because it's a technique that is spread. And it's used very often for mode shape analysis in the automotive area, on cars, on engines, and so on. And it's very accurate, can resolve very tiny displacements.
Very nice.
I don't have, do I have an example? I have a slide with examples. I don't have a video.
No video anymore.
We have here a shaker. Actually, I have only found one example in YouTube where somebody has used a shaker to measure the eigenmodes of this beam. And of course, this looks like a very stiff beam, so the amplitudes will be very tiny. I don't know exactly what was the frequencies here, but you see the the result of the laser vibrometer can be used, for example, to distinguish different modes. On the left image in the bottom, you see the first eigen mode. On the second image, you see the second eigen mode. And it can resolve really very tiny displacements.
Nice overview. So I think we've seen the different technologies available for optical measurements, different setups. So we started with the handheld stroboscopes, been going through different options. So could you summarize the requirements generally?
Yes. Actually, I have a slide to sum up the requirements. And all these techniques are optical techniques. All these techniques require that you have optical access. So you cannot look behind an object. Otherwise, you need to stand behind the object. So you need to place your strobe light and the human eye to have optical access. The same is for the strobe cam, for a high-speed camera, DIC with high-speed camera, and the vibrometer. They all need optical access.
DIC with high-speed camera has been random excitation. Right?
Exactly. This is why I added it to this table, because we get different information, or we can use it on different applications. That's better to say. And on a strobe light, we in addition need to know the shaker frequency, or we need to find it by tuning the frequency of the strobe light. So this can be time consuming to find it if you have no idea about what is happening. But typically when you use a frequency generator together with a electrodynamic shaker, you know with which frequency you run your test. So
and you need
to input the shaker frequency on the strobe light. The same works with the strobe cam. So either you manually enter the shaker frequency, or you use this microcontroller unit that reads the COLA signal from the generator and is automatically doing the frequency sweep and so on.
Yeah, nice.
A high-speed camera needs nothing. In principle, you can run it.
Trigger maybe for shock testing?
For shock testing, a trigger is good, yes. If you want to use it for shock testing, if you want to use it on a random test or on a single frequency, you just run it. You need to ensure that your recording time is long enough to have the vibration in it. Yeah. So if you have an eigenfrequency of, let's say, 0.1 hertz, which is one movement every 10 seconds, a high-speed camera cannot be used at full resolution. You need to reduce the frequency, the recording rate of the high-speed camera. Otherwise, a high-speed camera has maybe only a second or half a second recording time at normal setup, at full resolution and full speed. If you use 3D DIC, you either need to know the shaker frequency and enter it manually, or you use also a synchronization technique like we use in the strobe cam to have a phase synchronization.
Okay.
3D DIC and high-speed camera, of course, we have used it in this example for this pink noise, but you can use it also for a shock test. If you're using it on a shock test, again, a trigger signal would be nice. Otherwise, you might miss your event.
Okay. So we are almost through the presentation and almost through our assigned 60 minutes. So it might take a little bit longer than 1 hour. Please stay with us. Another question, of course, is many of our customers are using shakers in a test house, in an environment where they really need to prove the data is reasonable, showing the right, correct results. So the accelerometers for the shaker need to be calibrated. So does the vibration controller. We've seen that you can identify tiny displacements. So what about calibrating optical systems?
Yeah. It depends what you want to do with the system. And a strobe light, you cannot really calibrate. Of course, you could calibrate the time base. If you want to use a strobe light to measure the frequency of something, then the time base must be calibrated. I have missed to write this in the table. On a strobe cam, you don't need to calibrate it because it's used for visualization. But when you start to do post-processing and want to get quantitative displacements, you could use a simple calibration technique with a let's say a ruler to get the measures in millimeter, and you can certify those calibration plates, so you get a DAC certificate if you want.
Really?
So only for visualization you don't need to calibrate this technique. Also with a high-speed camera, if you want to do post-processing, measure displacement, you need to do some scale calibration for it. And of course, a high-speed camera, it has its own calibration in terms of time base. Yeah. So for every high-speed camera, you get a certification about the accuracy of the time base. 3D DIC, as we are using two cameras, the setup is very flexible. You can use it for small and large objects. You need to calibrate it with a checkerboard plate, and this checkerboard plate, we can also get a DAX certificate for it. So this is proven way to do it. And a major advantage of our DIC system is also that we get the standard deviations for all displacements and coordinate values. So we are always sure how good the measurement is. The same is for DIC and high-speed camera. So it works the same like DIC with static cameras. And the vibrometer, I'm not an expert on vibrometers. I'm sure that they are somehow calibrated in terms of frequency, whatever. But probably we as an end user, we will never calibrate it. It must be a calibration during the manufacturing.
Very good. The limitations and maybe a wrap-up summary from you about the technologies, maybe some ballpark figures about.
Put a slide together with that. What are our technical limitations and practical limitations? So I have added in this table only the key points that I see. So for a strobe light, it works only for a visible motion amplitude. If the amplitude is too small to be seen with a human eye or with a, let's say, loupe. I don't know what is the English word of loupe. Maybe there are enough people to understand German. So a strobe light can only visualize large enough movements. It's the same with the strobe cam. The motion must be large enough than a pixel, let's say, to be seen. Unless if you do post-processing, you can increase the sensitivity by a factor of 100. The same is valid for high-speed camera, for DIC, with high-speed camera or with static camera. The practical limitation I have already told about the Nyquist frequency, which is important if you use high-speed cameras together with DIC, and probably there is also some limitations on Vibrometer, but I would guess that it's anyway not dedicated really for electrodynamic shakers because it's too sensitive. It will also measure large deformations, as far as I have understood from this technology.
And your summary about technologies? Is it possible to just
summarize? Last minute summary. So
last slide.
One slide. Strobe light is probably the lowest cost solution, unless you want to go to very high frequencies and unless you might need a lot of lights that is also used for rotation events. A strobe cam is very nice for visualization, but also provides videos, so you can easily use it for reporting. You can send a video to your customer, hey, listen, it's moving at this frequency. Here you can see it in detail. You need to improve whatever. High-speed camera, typically only necessary to use for shock tests. 3D DIC is a quantitative technique, so it's probably the most accurate technology if we don't think about Vibrometer. It provides a lot of information. It's a full field information technology. We use it for model analysis, and in combination with a high-speed camera, we can even use a DIC system for impact testing, for white, pink noise, and so on. So can go to more dynamic singular events. And Vibrometer, my summary is it's very sensitive and can go up to very high frequency. It's also very, very expensive. So probably for a 3D laser vibrometer for 3-axis, you need to spend more than 200,000 euros, maybe even more.
So, yes. Thank you very much. I think that's the end of the presentation.
Yes.
So thank you very much. It's very interesting also to see what happened in the field of optical measurement is really surprising. So that just from recording with the camera, things that are going on, you can, with the post-processing capabilities, you're not only able to evaluate frequencies with maximum amplitude, you really have some figures, some real displacement. And what I didn't know before that presentation of today, so this is my takeaway of the day, that with post-processing you can increase the sensitivity by large amplitude, like what did you say, 50 to 100 times more accurate than with the bare eye. So it's always a single camera going live. So really great. I just can see, so we are at the end of our presentation. So if you have any questions, we're here for you. Ralph is here as an expert to answer your questions. The videos, yes, we do have the videos on YouTube. I think we can share the links later.
Yes.
Not done that yet, but we can send an email to give you access to the links with an email campaign later. So I've started sharing the presentation file for you to download. I hope you are able to access it. And if you have any more questions after the very nice presentation, thank you, Ralph, again.
It was a pleasure, thanks.
Then let us know. Let us know. Goes well with it started to snow outside again. So I have a question from Thomas.
Thomas, thank you, magnifying glass. That was the right word. So, sorry, Martin.
No problem. I didn't know that either. Sometimes you're so... How do you assure that peak amplitude from a trigger signal matches peak response from specimen the moment when camera takes a snapshot? There is a natural delay between peak trigger signal and peak physical response of the object. In other words, how to match peak control signal to peak displacement of deformation.
Actually, it's not really necessary to do that. Of course, if you have a sinusoidal signal, it's not really necessary to get the peak in detail because you have enough information to reconstruct your sinusoidal displacement. And actually, neither a strobe cam nor a strobe light is always getting the peak point. Even with a high-speed camera, an image might be just before or after the peak. It's not ensured. You cannot. And there is no electronic technology, as far as I'm aware of, that can really accurately predict that there is a peak, now trigger. Because triggering means the exposure time starts and it's already too late to get the peak. The exposure time starts after the peak. But all these technologies provide enough time information to reconstruct a movement. And that is accurate enough in our experience.
I think, I would guess, as long as a phase difference between the trigger signal and the recording signal is a constant, it doesn't matter what your specimen is doing.
Exactly, and this is what, if you want to have again a look in the videos, you will see that there is in the Strobe Cam videos always the frequency displayed, and the frequency is slightly varying because the controller is permanently measuring the frequency, and there is always some measurement inaccuracy. Okay, yes, thank you, if you run it. So you see the frequency is the first value, it's slightly varying, and the last value, the second value, is the phase. And you see the phase relation, the phase delay, let's say, to the 0 point of the sinus is always fixed. The customer, the user can set up how fine he wants to adjust the phase. And the interesting thing is, I have not talked about that, but we can use nowadays a high resolution camera, let's say 5 or 12 megapixel camera, to measure a mode shape at 1 kilohertz. So the camera records only 10 hertz because a high resolution camera is very slow in its frame rate. So we can use a slow, high resolution camera for high frequency because the trigger is so accurate. It works, of course, only when the sinus is a sinus for some fractions of seconds. So the image system needs always to record a few images to digitize your sinus. But with this, it's possible to resolve very tiny displacements by using high resolution cameras. It provides a lot of quality, image quality. So we can actually, with the Strobe Cam system, you can forget this Nyquist theorem because the trigger unit, it is much more higher resolution in terms of phase synchronization accuracy than a high-speed camera can do.
Nice. Thank you. Just looking back at the script from the beginning when you started and founded Limes in 1998, now almost 23 years later, what is, from a technical point of view, what is the biggest change, the biggest development in the technology?
Actually, it's both. It's both hardware and software. When I worked at university, I have already developed camera systems. So let's say 25 years ago, a little bit more even, we have used cameras with 720 by 400 pixel. So very low resolution, very low quality, very slow.
I remember the first webcams, very small.
So if you do DIC analysis 25 years ago, you needed maybe to wait half an hour to analyze one image. Nowadays, we can analyze one image in half a second. So the computer acceleration, the software development, it's parallelized now. So you can analyze an image parallel with all CPUs. And the camera technology, both is responsible that we are at the moment where we are. And in terms of camera resolution, I don't expect that we get the same steps in the next 10 years that has been done in the last 10 years, because it probably makes no sense. Probably in 5 years we see that it makes sense. Probably it makes no sense to go to 100 megapixel cameras. The data amount is so huge to handle those images. But we'll see. 15 years ago, I have predicted that people are doing DIC post-processing on their watches.
Okay.
In principle, you can do it on your smartphone, not yet on the watch.
Okay, yeah, I think when IBM came up with the first computer in the 70s, they would say, oh, we need a maximum of 5 computers all over the world, and that's it. And that's been proven wrong. Yes, so everybody, thank you very much. I think that's it for today. no more questions. Thank you again, Ralph. It was very, very interesting. I really enjoyed the presentation today. And if you have any questions afterward, then please feel free to contact us, Ralph, myself, anytime. And have a nice day.
Thank you very much again, Martin, for organization, for the invitation. Have a nice day to all the people still in the audience. And yeah, take care.
Thank you. Goodbye.
Yeah. Thanks. Bye-bye.